There are many things in nature that obey what we call linear relationships. In other words, they form straight line graphs. One of those things is something that we call the spring constant. A spring, such as this balance here, can be stretched with a certain amount of force, and then the force can be increased. I got it upside down. But it takes a certain amount of force to stretch the spring an additional length. It turns out that a certain amount of force will stretch the spring a certain amount, and then a more amount of force will stretch it even more, and that will increase with a linear function or something very close to it. I have two demonstration apparatuses to show. One uses springs, and because you can't get close enough to see the readings, I have already obtained the readings and plotted them out. What we have here is a force in newtons. In other words, these masses that I'm putting on here produce a force in newtons, and I've already done the translation, and they stretched the spring a certain amount of length or distance. For instance, right now the bottom of this empty pan, I put it on the 0 mark. This is a centimeter scale, and it's got little millimeter divisions. I put it on there, that's now, I believe, 50 grams. That's 50 grams, and it stretched it a little bit. I plotted that point here. Actually, it's not 50 grams, it turns out to be 5 newtons, okay, doing the translation. So I plotted it there. Now I add another 5 newtons to make a total of 10 newtons down there, and I plotted that point. It stretches it about a little over 3 centimeters. Now I'm going to add on another 5 newtons worth of force, and it stretches it about it stretches it about 4.5, and actually 4.8 centimeters. And then finally, I don't want to overstretch the spring because then it won't obey a linear relationship. I'm going to put another 5 newtons, that's 20 newtons of force up there, and I stretched the spring about, this came out to 6.6 centimeters. Now why did I set it up with the y and the x this way, the force, the stretching force, and the length it stretches it? Because the spring constant shown here is a ratio of the force in newtons against the spring, whatever spring you have. And by the way, it doesn't matter if it's a compressional spring, one that you press, or one that you stretch. They obey the same law. The spring constant is expressed in the force applied to the length you get. In other words, the force applied to the length you get of the spring. You apply a greater force, you get a greater length. The actual units are newtons per centimeter in this case. In English system, they would say pounds per inch. If you had a spring, you press it with 100 pounds, it might compress 2 inches. But that's a very linear relationship, and that figure is in the box of springs when you get the box of springs. They already have figured the spring constant, which, if you haven't imagined already, is how strong the spring is. An automobile spring is very strong. You have to press on it with thousands of pounds, or at least hundreds. This is only taking some grams, a few newtons. So the force per length tells you, in whatever system you're working, it tells you how much force that you have to apply to get a certain length. And you can use that as a predictor. Now, in this particular case, I'm using a rubber band. You can do the same experiment at home by finding some rubber bands and finding some place to attach them. And you can be imaginative there. You don't have to use a hanger. We're using a little hanger here to hang aluminum. It's hardly any mass at all. You could use a paper clip that is bent open. And for masses, you can use washers, big fender washers. And it works this fine. The scale can be nothing but a ruler a metric ruler taped onto something so that you can measure how low the masses go. So you can make one of these at home very simply. Now here I got a rubber band, and I'm going to do the same thing. This is something you can do at home. I put a large mass here. This is 200 grams. And that would translate, let's see if, I forgot how many grams, 200 grams here would be actually 20 newtons of force. So I'm putting that much on, and it stretches it down. And now I'm putting more on this rubber band, and it stretches it even further down. And I could put more on. I might break the rubber band. I've got actually two holding it because I didn't cut the rubber band open and just use one piece. I've got two, so you would figure that if two of these stretched it down to here, that a single one would go twice as far. You would have to experiment with that at home, but I think it's easier just to use a standard rubber band without cutting it or anything like that. Just get little ones, big ones, long ones, and see how much force it takes to stretch them certain lengths. And you could make up a little graph just like the one that I've got here, and you will see, as you can see here, it is pretty much a linear relationship. This function right here, I'll draw a curve, where the rise over the run would be this, and this would be length. That's why this is in length, and that's in force units. So we've demonstrated how you can get a very good constant by using a simple spring or even a rubber band to find out if it is a linear relationship. Thank you for viewing.